In the previous video, we looked at examples of how reinforcement learning can be used in real-world applications, such as playing games, coordinating traffic, and teaching cars how to drive themselves. While these are all great examples, they are still a little abstract, possibly leaving you wondering, well, how does this whole reinforcement learning thing actually work? So in this video, we are going to take a deep dive with a practical example of reinforcement learning through a game. What you see here on the table is a very simple 3x3 board. Similar to chess, we have two teams on opposite sides of the board. In our case, it's orange Pecky and blue Pecky. For those who are wondering, who is Pecky? Pecky is the mascot of Amazon, with the name being a nod to the peculiar ways we do things here. Anyway, getting back to business. The pieces can only make two types of moves. Straightforward one square to an empty square, or moving one square diagonally to take the opposing team's piece, and the captured piece is then removed from the board. The keen-eyed might realize that these moves are the same as a pawn piece in chess, and this game is actually called hexapawn, but we're going to call our game pexapawn in honor of Pecky. So how do we win this game? Well, the game is won if any pieces make it to the third row, if all of the opposing team's pieces are captured, or if the team achieves a position where the opposition cannot move. So this does seem like a trivial game, but that's not the point. We're going to use reinforcement learning to teach a computer how to play this game, and hopefully it should become so good that it can consistently win against a human player. But this is no normal computer. It is actually a series of 24 matchboxes. This idea was conceived in 1961 by the artificial intelligence researcher Donald Michie, who developed something called the Machine Educable Noughts and Crosses engine, or MENUS, to play human opponents in noughts and crosses. It could adaptively learn how to play and eventually win using reinforcement learning. This was implemented as a computer consisting of 304 matchboxes. Now, I don't know about you, but that sounds like a lot of matchboxes. So 1 year later, Martin Gardner created a simpler version on a 3x3 grid, which only uses 24 matchboxes. And that's what we're implementing here. But you might ask, matchboxes aren't computers. How can they learn? Well, when we think about computers, they are really just devices which can store, retrieve, and process data. So let's look at how our matchbox computer can fulfill these functions. You'll notice on each of our matchboxes there's a number and there's a diagram. The number denotes the move of the game. In hexapawn and pexapawn, the human always goes first, so the computer always goes second, the player third, the computer fourth, the player fifth, the computer sixth. So let's say the computer wants to evaluate possible options for the fourth move of the game, which is the computer's second move. It will look at the boxes with the number 4. Now, the diagrams on the matchboxes show the possible states of the game board at that point in the game. So the computer finds the diagram that matches the actual game board and then uses it to determine its next move. Now that sounds complicated, so let's do an example. In our game here, the computer is orange and the human is blue. So let's say the game has started and the human has made their move. All right, so now what we do is we look for the matchbox that matches the state of the board for move number 2. So what we can see here is we only have 2 matchboxes, and the state of the board that matches the diagram is this one right here. So what we do is we grab the matchbox, and inside the matchbox, what you'll notice is there are some colored beads. So in this case, we have 3 colored beads: green, red, and blue. And they match the arrows on the diagram, as we can see, green, red, and blue. So what we do in order to determine the move is we give our matchbox a bit of a shake. We tip out one bead. In this case, a red bead came out. And then we look on our diagram and we follow the move that it tells us to do. So in this case, for a red bead, we want to move this pecky here down one position to here. And we leave that bead out for the moment, so we'll just pop it on the top of the box. So now our human player makes another move. So let's say our human player actually takes that piece just there. So the computer's piece gets removed from the board. And now we have a look at our matchboxes again to see what diagram matches. So let's see here. So we've got two blue pieces there. So it looks like this matchbox over here has the number 4 on it. So this is the 4th move of the game. So the 2nd move of the computer. We have our two computer pieces up here, have our player pieces here. All right, so in this matchbox there are also 3 beads, green, blue, and red, matching the green, blue, and red arrows on the diagram. We give it a shake, tip out one bead. Whoops, it was a blue bead that came out first. So on our diagram, what we're going to do is we're going to move this pecky piece to take the player's piece. So there we go, pop our matchbox back there with the bead on top. Now the player makes a move, but in this situation, the player actually can't make a move. They're blocked in. So in this situation, the computer has won, so we don't actually make it to another round. So what we can see here is the computer has won the game, so it has made good decisions. And we want to reinforce that. So what we do is we put all the beads back into the matchboxes and reset them for the next game. So we'll pop our beads back in. The computer made a good decision, so we want it to make those decisions again. Like so. So now let's do another round of the game and let's see what happens when the computer actually loses. So we have our game board reset and the player always goes first. So let's move our player's piece like that. Right, so we have a look at our matchboxes to see if we can find the state of the board that matches these. So it's going to be the matchboxes of the 2. So this matchbox matches the state of the board. So this matchbox inside it has a green bead and a blue bead. So give it a shake, tip out one of the beads. It's the blue bead. So following the diagram on the matchbox, what we're going to be doing is we are going to take this computer piece and take the player's piece, like that. Pop our matchbox back and pop our bead on top of it. Right, now the player can make a move. So in this situation, well, the player can probably take this piece here, the computer's piece. So we'll do that and remove that from the board. So now it's the computer's turn. So let's look for the matchbox that matches this board's configuration. Looks like it will be this one here. We have our 2 pecky pieces there and our blue pieces here. So this matchbox inside it currently has a red bead and it has a green bead, so let's give it a shake. Oops, whoa. Right, let's try that again. Okay, the green bead has come out. So we're going to move this pecky piece down one, like so. Put that there. And all right, in this situation, the computer's also won. So not much we can really do here. So let's reset the game and try again to see if we can get the computer to lose. So we'll pop our beads back in because again, we want to reinforce that good behavior. All right, let's try again. Let's see if we can get the computer to win. Oh, sorry, I should say the computer to lose this time. So player goes first, move that piece there. Let's look for the matchbox that matches the state of the board. So it's actually this matchbox here. it's just a mirror image of what's on the board. So that's why we don't have a second matchbox for this situation. So let's grab this, give it a shake, and come on. Got a blue bead that came out. So following what's on this matchbox, we're going to move this pecky piece down one, like so. Just pop that back there with the bead on top. All right, now the computer makes a move. So, sorry, I should say the human makes a move. So let's take the computer's piece like that. All right, so now let's look for the matchbox on move number 4 that matches the configuration of the game. It looks like it is going to be this matchbox right here. Again, it's just a mirror image of the board, but it still matches, as we can see the L shape of the blue pieces there. So we'll grab this matchbox, give it a shake. Oops, the pink came out first. I should say the red came out first. So what we're going to do is we're going to move this pecky piece down here, like so. So we'll pop that there. Now it's the player's move. And look, the player will be able to win because they can just move one forward and they made it to the third row of the board. So in this situation, the human has won and the computer has lost. So the computer has made a poor decision. Now we want to discourage this decision in the future. So what we do is we confiscate the bead which represents the last move and do not put that back into the matchbox. So that was this matchbox here, the last move the computer made, and that move resulted in the computer losing the game. So we don't want it to do that again. So we remove this bead and don't put it back. So I'm going to just put it over here to the side. So as you can hopefully see, our matchboxes are essentially the computer. They store beads along with information about future moves, and we can retrieve a bead which in turn informs the processing of how to move the computer's piece on the board. And by confiscating beads that lead to bad decisions, which was the computer losing the game, we're essentially punishing bad behavior and discouraging it, the key concept behind reinforcement learning. Let's have some fun now. Let's play the game over and over again to see whether the computer learns how to play and refines its strategy over time. So now we've played almost 20 games, and when we first started, I was winning quite a few of the games. We can see H here for human. But then things started to change and the computer started consistently winning, denoted by C. Now this didn't take too long, as our approach to reinforcement learning in this situation was to essentially punish the computer for losing the game by removing the beads. You can see all the beads over here. In fact, we actually want the computer to lose games so it learns faster. So this approach here is efficient when the computer is versing a good opponent. So apparently I'm quite a good opponent at Hexapawn. Another approach we could potentially take is, instead of punishing the computer, we could reward it for good behavior. So when the computer wins a game, we add another bead of the color which made the winning decision to the matchbox. Now this will increase the probability of that decision being made again in the future and reduce the probability of other decisions being made. Of course, we could also combine both approaches, rewarding the computer for winning a game by adding a bead and punishing the computer for losing a game by removing that bead. Now, while this is very much an academic exercise, originally devised in the 1950s as the researcher didn't have a computer readily available, it does go a long way to demystifying how reinforcement learning actually works, beyond the simple explanations which are often discussed concerning actions and rewards. I hope that you've enjoyed this video looking at Hexapawn, or in our case, Hexapawn, and it's perhaps inspired you to build your own Matchbox computer to learn a bit more about how reinforcement learning actually works.